Hi everybody. Sorry I'm late today. Actually, I kind of missed a couple of other times. Anyway, um, but we're carrying on. So we're left off at we covered the rest of scoping rules last time, and now we're talking about traits. And it looks like we can no longer scroll down. Yay! Okay, traits. So we've kind of encountered traits already. We have created traits, I guess. Mostly to do with like, and they seem to be like functions we can attach to objects, I guess. So we're going to find out more stuff, I guess, about this. All right, let's see. A trait is a collection of methods defined for an unknown type, self. Okay, they can access other methods declared in the same trait. Okay, that's cool. All right, so we have private methods, but it's an unknown type self. Okay, traits can be implemented for any data type. In the example below, we define animal, a group of methods. The animal trait is then implemented for the sheep data type, allowing the use of. Oh, okay. So we were doing implementations of pre-existing traits. So this is like, so in C#, this would be like an interface. We say, okay, this thing is, has these methods associated with it, and then we can implement that interface for, whatever object. Okay, cool. So implement sheep is naked shear. Okay. And then we can implement animal for sheep, and then we can have, so okay, so this is like, so this looks like we can create an implementation for sheep which has specific additional methods in it, and then we can attach this animal and we implement animal. Okay, fair enough. So why would we want to do that? Okay, this type of annotation is necessary in this case. Dolly sheep equals animal new dolly. Try removing the type annotations. Okay, let's see. If we remove sheep, right, we run that. Okay, here we go. Type annotations needed. Dolly type must be known at this point. Consider giving Dolly an explicit type. Form version is this error. Okay, so all right, it tells us, hey, I don't know what you're talking about. So because animal is a, oh, this is interesting. Okay, so animal is a particular kind of, so we don't have a class for sheep. Okay, we don't have an implement. All right, how am I to interpret this? Okay, so we need to say, oh, I see, because the struct is sheep, and we have an implementation for sheep, and we have animal for sheep. But we actually need to say this is a sheep. And then we can attach this animal to it and give it a name. So name naked is false, sheep is name. New. All right, so we can new creates a. So, see, I keep seeing new and thinking it's a keyword, and it's not. It's a method that, or a function that they've implemented that returns a sheep. Okay, which I guess kind of makes sense because, well, then actually why? Why do you have to make it explicit? Because new is going to return a sheep. Oh, but there could be other implementations of animal for other animals. And so at this point, you bump into animal new and you go, well, is that the sheep implementation that I need to execute, or is that the deer or the cow or the whatever implementation of animal? And so it's unclear which one without specifying something, right? So that makes sense. Okay, got it. Now, interesting though. All right, Dolly. Yeah, Dolly. Talk, sheer talk. Bah gets a haircut. Bah. Okay, and talk. Oh, is naked. Question mark. Otherwise, exclamation mark. All right, fair enough. And the is naked comes from the implementation. So we can call, oh, self is naked. Okay. So in the implementation of the trait, we can call things that are inside of the implementation, or the implementation of sheep. That's interesting. Huh. That's interesting. That's interesting. Okay, and default trait methods can be overridden. So talk. So yeah. Well, yeah. Oh, overridden. Yeah, because here we have implemented. So it's, yeah, okay. So it's not really an interface. A base class? Yeah, but I don't know. Yeah, okay, so it's some kind of combination of the two. Where we can say, we can implement things, provide default implementations, but also just define signatures that we can, okay. All right, cool. All right, fine. All right. Derive. The compiler is capable of providing basic implementation for some traits via the derive attribute. These traits will be manually implemented. Can still be manually implemented for more complex behavior. So we've bumped into this derive thing. Clone, copy, hash, default, debug, comparison traits, equal, partial equal, ordinal, partial ord. I assume that's ordinal. Don't know for a fact. Centimeters. A tuple construct that become compared. Drive, partial equal, partial ord. Inches, a tuple struct that can be printed. Derive debug. Oh, right, that's where we've seen this before. Derive debug. Oh, yeah, there it is, debug. Okay. Implementation inches. Okay, seconds. A tuple struct with no additional attributes. Okay. Seconds can't be printed. It doesn't implement the debug trait. Try uncommenting this line. Okay. And we get component error seconds does not implement debug. Here we go. Add derived debug to seconds or manually implement debug for seconds. So if we try to manually implement debug for seconds, what would end up happening here? There. So implement impl debug for seconds. Now, how do I know what? How do I know what is the method I need to implement? Because it wasn't obvious. All right, let's run this again. See if the error gives us a clue as to what we need to implement. Okay. Consider importing. Oh, yeah. Debug is not a trait. Consider. Okay, let's bring that one in. Okay. Okay. Let's try running that. Okay. Missing format in implementation. Okay, so it is. Help. Implement the missing item. Format. Oh, okay, look at that. Thank you. Results. All right. Let's implement that. Why is there one angle bracket? I don't remember this syntax. All right. Oh, there's my C sharpness coming through. All right. What to do here? So, all of this stuff we've done, and I haven't a clue. But we've implemented format before for the non-debug case, so I'm guessing it's going to be a similar kind of pattern. But I don't really know what I'm doing here. But the underscore is like a type, right? All right, let's go look at, let's go over and find, where are you? There you are. Let's pull up one of the old ones. Open folder. Generic trait? No. Print complex. Let's have a look at that. Does it have... Oh, we just did drive debug, but... Oh, here we go. Implement format binary. Implement format display for point... Oh, maybe we should do it that way. Implement format display format, right? Because this one, yeah, we use standard format, and then we implemented but this, yeah. Oh no, but this was we did the debug version and then we did the regular version. Okay, so maybe okay, and then F formatter format result. Okay, and then write. So yeah, this was F. So let's go back there, and let's just make this F. I'm not sure. What was, okay, so how did that go? It was format ampersand self F mutable formatter. So mutable formatter that ampersand self, that's the same. Result just result, I think, because that's what we had over here. And let's use write, the write macro. Hello. All right, and let's run this and see what happens. Cannot find the type formatter. Okay. Oh, okay, yeah, so I just haven't brought that in. Expected 2 generic arguments. Oh, T and E. Okay. Oh, all right. So maybe what he had here was, all right, T, E. Let's just do that. Run that. All right. Missing tokens in macro arguments. Oh, right, because, yeah. Oh, cannot find T in this scope. No, while trying to match comma, cannot find T in this scope. Here's a format type parameter. Cannot find E. Note similarity trait equal not defined here. Oh, it was trying to interpret that as an equal. Oh, right. We did that weird thing. Or we did the, Yeah, I don't know. All right, so this needs to be F, I think, like that. Let's oops, cancel. Let's try that. All right, so what have we got here now? So that worked. So that first issue is resolved. But here, you might be missing a type parameter T. Not found in this scope. Okay. Okay. All right. Well, let's do implement. Because I remember this as being something. Type parameter T is not constrained by the implementation trait self-type or unconstrained type parameter. Type parameter E is not constrained. Oh dear. Yeah, I don't. Now I'm lost. Because it's. So when I get rid of all of this, it says. And I run this. It says that, hey, expected 2 generic arguments. Help add the missing generic arguments, T and E. Oh, hang on a second. But But if I put them in, then it says, oh, I don't know what those are. So do I need to specify something? Okay. All right, let's try. Rust custom impl debug. Ooh. Actually, the second one. How to implement a custom. Okay, here we go. Yeah, it says there. Oh, yeah. Getting the two things wrong. So according to then, yeah. Okay, so they're saying, well, don't do that. Do this. Format debug, use standard format, and then format debug, format result. Okay. Oh, because the plain result type does have two generic parameters. The format result has none. Oh, okay. Okay. All right, well, let's try this. So if I say, and this is, sorry, right, because this was like, we did format display here, right? And then format result and format formatter. And we use standard format. So let's follow this example here. So I tried to do something different, but clearly I'm not doing the right thing. Okay. All right, let's go back to here. Instead of using this, we're just going to do that. Use standard. Okay. Well, oops. Well, although this, the example in, where'd it go? Oh dear. Where did it go in the browser? That one. It doesn't give me it does standard format. Okay, so use standard format. Okay, so use standard format. Okay, so we don't need these anymore, and instead we're going to say format debug, font debug, and then this is format formatter and format result. And let's run that. And okay. 1 second looks like hello. Right, because I did an implementation of the debug format. Yes, sir, I did. Except I just dumped out a constant here. Okay, so I got that working. So now, what I need is what? I think, if I remember correctly, yes, it's curly brackets and then self dot. What? 0? It's the first one. It's the only one. It's a tuple. I'm guessing. Did I do that right? All right, let's find out. The second looks like 1. 1 second looks like 1. Huh. 1 second, 1 second, seconds 1. Yes! Okay, so it took a little doing, but it's done. All right, so I can implement my own debug formatter for a particular thing. Okay, cool. Let's see also derive. So what was this? All right, so I implemented the derive. We can do all these other guys, equals and whatever. I don't know. What is centimeters? What does this mean? Derive this one and that one. Centimeters. What's going on with centimeters? Oh, here we go. Foot 2 centimeters, less than meter, smaller, bigger. Oh, well, there's an interesting bit of syntax I don't recall seeing before. Using if like a ternary operator. And the return value of the if statement. Interesting. That's interesting. So yeah, instead of like colon or question mark colon, you can write that, which makes it a little easier when you're writing something complicated, because I mean with the you know, the question mark colon operator, the ternary thing, after like 3 levels or 2 levels, depending on how you want to look at it, it gets too complicated to read. But I can see this being much easier to read for, you know, because it's wordier, more things. Okay, and I have to remind myself that if statements don't require brackets. Brackets, at least they don't appear to. I think I remember something about that before. And then 1 foot is smaller than 1 meter. Foot 2 centimeters. Foot inches. Okay, so 2 centimeters converts. Okay, 2.54. Sure. It returns a centimeters. Okay. And partial equals partial ord. What's the difference between seconds can't be compared? It doesn't implement partial equals trait. Oh, okay, so that's cool too. So if I uncomment this and then run this, okay, all right, yeah, here we go. Unnecessary parentheses. Oh, okay. And then, oh, okay. Here, first it tells me about the unnecessary parentheses. A lot of information about the unnecessary parentheses. Like there's a warning, there's help, there's an. Oh, now it says, okay, that's right. So that whole thing here was about the brackets, and then this cannot be applied to seconds. And then this might be missing for seconds. Okay. Must implement. Consider annotating with. Okay. All right. So then we can take that. Well, I like this. I like these error messages because I'm able to almost get to the right answer, but not quite. Remember what happened here with the implementation of debug. It kind of led us down the wrong path for this, because it gave us a signature that wasn't correct, right? It was like, hey, basically the signature that guy in the Stack Overflow tried to use, we tried to use the same thing, right? Because it said, Well, do this. So, okay, fine, we'll do that. And then couldn't do that. But here, okay. All right, so now if I run this, but this case, I think it's going to give us the right information. Yeah, this is true. So we didn't, there's no output, but there's also no error. So this evaluated correctly. Okay. Yeah. So I wonder what partial OR does. All right, let's move on. Enough bashing with that. So a couple of things, let me just, before I do that, a couple of things that are interesting. This is now starting to get more interesting, right? Because we're able to convert to centimeters and we're able to return self. We call the 2 centimeters, and that returned here, inches, foot, 2 centimeters. That returned a centimeters object, but it didn't complain about ownership, which is kind of interesting. Here, though, that inches equals self. Now, what happened here exactly? So we're borrowing inches? Is that what we're doing? So ampersand self. Yeah, so it's like inches. The object inches. Right, foot is an inches object. And we were able to create a borrowed version, and then we're able to grab the, but all right, let me just ask this dumb question. Would we not have been able to do self.0? Yeah, we're able to do self.0. So why do this when we can do this? And okay. Because here in the debug we're using self.0, right? I guess we could have written this instead and said, but I guess maybe because I want it to be called inches, I want to extract, but couldn't I have just said, if I wanted the name, couldn't I have just said and then let's try that. Yeah, that still works. Just make sure. 1 foot is bigger than 1 meter. Yes, because I multiplied by 12. But now back to that. And 1 foot is smaller than 1 meter. Yes, so I am actually executing code that is changing. So I don't really understand why that was written the way it was, with the ampersand and the inches object, which then we extracted. What? Because self, I don't really get it. Why you would do that? Because wouldn't this isn't? I mean, if you needed a name for it, you didn't want to use self.0 because this was some really complicated thing you were doing. Why wouldn't you just do that on line 13? What I've got on line 13. Anyway, all right. moving on. Yeah, alright. I think we've extracted as much as we can from that. Returning traits with dyn. The Rust compiler needs to know how much space every function's return type requires. This means all your functions have to return a concrete type. Unlike other languages, if you have a trait like animal, you can't write a function that returns animal because its different implementations will need different amounts of memory. Fair enough, right? Because functions return values on the stack, and we need, I think, right? However, there's an easy workaround. Instead of returning a trait object directly, our functions return a box which contains some animal. A box is just a reference to some memory in the heap. Yeah, so instead of putting it on the stack, we can put it on the heap. And we return a reference. And a reference is always just the same size as a referenced size. Because a reference is a statically known size, the compiler can guarantee... Yep. Okay, Rust tries to be explicit as possible whenever it allocates memory on the heap. So if your function returns a pointer to trait on heap, good lord, you need to write the return type with the dyn keyword. Box dyn animal. Okay. Box dynamic. I assume dynamic. So a dynamic data type. So maybe it's a sheep, maybe it's a cow. All right. Oh, that's interesting. Random animal returns either a box of sheep or a box of cow, and we can use the noise because, right, we've got implement, right. We have a trait called animal, which implements a noise. And we implement sheep and cow, ba moo, and then it's going to tell us, okay, cool. Okay, sure. That makes sense. Makes perfect sense to me. So we have the interface equivalent thing here. We declare a sheep and a cow up here. Okay. All right. So declare sheep and cow. Say these are things that exist, and then we're going to, but they have no data, right? They're empty of data, but we're going to attach some functions to them, and right, if it's a sheep, if it's a cow, we create a sheep and a cow. Okay, cool. All right, that's fine. Operators can be overloaded. That is, some operators can be used to accomplish different tasks. Oh no, don't do that. It is possible because operators are syntactic sugar for method calls. For example, the plus operator calls the add method, as in a.addb. This add method is part of the add trait. Hence, the plus operator can be used by any implementer of the add trait. List of traits such as add that overload operators can be found in. Oh, that's interesting. Okay. Foobar, far boo. Add trait can be used to specify the functionality of plus. Implement ops. Oh, right, there's ops. Ops add bar for foo. Bar foobar print. Okay. What are you trying to say here? interesting. Foobar. What is drive debug foobar? Alright, I need to run this and see what this does. I don't understand. Oh, okay, so it's not actually adding things. Got it. Foo plus bar is foobar. Bar plus foo is barfoo. And so we've got two structures, foobar and barfoo. Okay, got it. That's what. So we're actually returning that structure. And because that structure is empty, it's just returning the name of the structure. Okay, so we're taking advantage of the fact that the debug will just output the name. Okay, so that's why we're outputting this, because it's just outputting the name for the debug. Okay, cool. So this returns the foobar object. This returns the barfoo object. This addition executes the add code, which returns that. The add code has a print in it, so that's why we get the first print line. And then this print line executes that line. Got it. Okay, yeah, that makes sense. All right, cool. Drop. Drop trait is only one drop, which is called automatically when an object goes out of scope. The main use of the drop trait is to free resources that the implementer instance owns. Box, vecting, file, and process are some examples of types that implement the drop trait. Drop trait can also be manually implemented. The following example adds a print to console to the drop function to announce when it is called. Well, this is convenient for droppable debugging purposes, because you can override the default drop with your own code, I guess. All right. Fine. Iterators. An iterator trait is used to implement iterators over collections such as arrays. The trait. The next element, which may be manually defined in implementation block. Okay. So if we have arrays, then we've automatically get a next. But if we've got some other weird thing, linked list, for example, or in their example, the Fibonacci, we can calculate the next. So we're implementing next. So Fibonacci cur next. Implement iterator for Fibonacci. The iterator trait only requires the method to be next. So implement iterator for Fibonacci. Type item is U32. Here we define the sequence using cur next. The return type is option T. Whenever the iterator is finished, none is returned. Otherwise, the next value is wrapped in sum and returned. We use self. Okay, right. So we're going to next. Right. So since the endpoint of the Fibonacci is never reached, we're going to always return a sum. So it's going to be cur is whatever next was, that's now current, and next is current plus next. Okay, yes, that's Fibonacci. So now it gives 1, 2, 3, 4 next calls. Next. okay, yeah, so we can call next ourselves. Or we can use the for loop to call next. We can do the Fibonacci. The take n method reduces an iterator to its first n terms. Get the first, okay. The skip method shortens an iterator by dropping the first n terms. Okay. Skip 4, take 4. All right, well, I wonder, all right, let's run this. I wonder how right. So how did it get to 3? It must have actually executed, the skip must have executed the first 4 things, but not done anything with them. Because otherwise, they would know to start at 3, right? So yeah, it's got to be. Yeah. Oh, okay. 0, 1, 2. When you say 3, right? I gotta remind myself. That's an iterator that generates 0, 1, 2. It's a length 3. That's a length at the other end of the dot dot, not the last index. It's the length. So length of 3. So if we do it 4 times, we're going to get a none. Oh, good. We don't get an exception. We get a none. That's nice. You know, C# would have puked on its shoes at runtime over that one. So yeah, this one, I don't know how it could have done it otherwise. So let me just check. So if we do a print here, let's just verify that. So if I do a print line self.cur, can I do that? Or is it going to complain? All right, let's try that. So if I do that, yeah, 1, 1, 2, 3, 5, 3. Oh, interesting. Oh, because this returns, I returned cur, I printed cur, and this returns, and then self next. That's interesting. I. Why is I? Oh, I is next. No. Because this is returning the whole object, current. And current is, whoa, wait a minute. Self.cur. Current is self.cur. I don't understand. So, here, 1, 0. 1. But how do we get 0 here? What's the angle bracket? Oh yeah, because here, this is the angle bracket. Angle bracket I. So this thing So this thing, take 4. It's printing 1 or 0, 1, 1, 2. And I printed 1, 1, 2, 3 because I was, all right. Oh, this is outputting current. And this is generating the next one. Oh, okay. All right, all right. Let's... Whoops. I don't want to do that. All right, let's run this again. Okay, so 0, 1, 2, 1, 1, 2. Here, when I output current, I get 0, 1, 1, 2, 3, and then I output 3. Okay, that makes more sense. So what was happening was I am outputting the next self, and this is displaying the current self, right? Because I save this, I say, okay, what's current? Save that away. And this is, what data, oh right, I don't know, I'm used to the other thing. Item is U32, okay. So anyway, yeah, so this is, now this is correct, because I'm outputting, that's interesting though. So I mutated self, but I output, okay, so I mutated self, I outputted current, and because I mutated self, then self now is the next one. So this is the mutation. This is the next one. But I'm outputting the current one. So whatever I started with. And so regardless though, it looks like there's no magic to skip over it. It's actually doing them and then just not displaying them. So the skip actually still executes this. So, you know, if you, that's something to be aware of, because, you know, if you're doing some expensive calculation and you go, oh, I'll just do a skip take, you don't realize that the first 10,000 are actually still being executed here, even though you're saying to skip them. So they're still being looked at. Now, that's because Fibonacci, we're doing a calculation. Because presumably, oh, I wonder. Yeah, but that's got to be what it's doing. Even in the, it's going to be like an index or something. So I wonder how it's implementing that. So when it does the sequence, and internally it's, you know, so it's calling next, I would guess that that's what that means, is that even if we did an iter dot skip 1, can I do that? Yeah, skip 1, and I get 337. So it's calling next. Skip is calling next, is what I'm thinking is happening here. So is it smart enough? I wonder. With an array, it could be smart enough to short circuit that and just say, okay, you don't want the first 10,000, because it seems insane to, if you have a 20,000 element array and you say skip 10,000, that it still calls next 10,000 times before it gets to your thing. But maybe not. Maybe there's, I don't know, if there's a way for skip to communicate. can we implement skip? Only requires that a method be defined for next. So that's true. Only requires, but is there a skip? I don't know. It's hard to tell because I don't know if this is going to. Well, we'll find out later. Because if there was a skip implementation, then we could do something like that, where we could go, okay, you know what? Let's not call next a whole bunch of times. Let's just figure out what the starting point of that Fibonacci sequence is, because I don't know this for a fact, but it's pretty sure there's a straight up calculation you can do instead of iterating to get to the starting point. Okay, infiltrate can be used in two locations, argument and return type. If your function is generic over a trait, but you don't mind the specified type, you can simplify the function declaration using infiltrate. For example, considering the following code: parse CSV document, buff read, source lines, map line for each line in the sequence, split on commas, then split map on each entry, and then collect all the strings in a row into a vector, and then collect all the lines into a vector. So parse CSV document is generic, allowing it to take any type which implements buff read, such as buff reader or U8, but it's not important. R is only used to declare the type of source, so the function can also be written as source impl standard IO buff read. Okay. What's the difference? R. Standard IO buff read source R. Okay. So we're shortening up the syntax a little bit because programmers are lazy. Okay, fine. Cool. Okay. If your function returns a type, impl my trait. Good Lord. Iter, cycle, iter, chain, into iter, Yipes. Impl iterator item 32. Okay. Yes, you're right. That is much easier to understand. There's no way that I would figure out what to type here correctly, I don't think. Well, maybe I will at some point in my life, but not today. All right. Combine vectors. Okay. Whatever. More importantly, so I'm just looking at what this does. This cycle thing here. Chain. Cycle. Alright. And so somehow all of this nonsense returns the next one. So we're iterating over V. We're chaining it to U, and which means that if we go 1, 2, 3, 4, 5, we'll just say next, and we'll get all of them. Yay. Some Rust types can't be written out. Okay. You had to allocate on the heap in order to return a closure, but now you can do it all statically like this. Impl function fin32 closure move closure. Oh dear God! All right, I've just lost the thread here. That's fine. So infiltrate is handy. That's all I'm going to get out of this right now. It's handy when you're doing complicated things. I'm not doing complicated things yet. Clone. The default behavior is to transfer them during assignments or function calls. Sometimes we want to make a copy. Clone trait helps us do exactly this. Implement the clone trait. Okay, we're copying clone. Pair. Box that, box that. Dot clone, where's dot clone? Pair is that. Moved pair. Okay, and we lost it. We can't get pair back because we moved it. But if we moved pair dot clone, then we have a clone, and then we still have moved pair has been dropped. Oh, really? Oh, because we dropped right here. But the result from clone can still be used. Okay, so if we run this. Okay, so we have moved. If we try to uncomment this and try to run it, we get an error because it's been dropped. But if we remove the drop and run it, then we have the moved one, the copy, and the clone. Right, the moved. Right, we have cloned. Right, we have cloned. We have the copy from the moved. And we don't have the original anymore because this has moved it. But if we cloned it, we'd have another copy. Okay, fair enough. Cool. Super traits. Oh no, Rust doesn't have inheritance, but you can define a trait as being a superset of another trait. Trait student. Trait person. Trait student person. Person is a superset of student. Implementing student also requires you to implement person. Trait programmer. And we can add two together. So comp sci student is programmer plus student with a get username. So then comp sci student greeting, Dyn computer science student format. I attend my favorite languages, my get name, student name, university. Okay. Yeah, okay. We don't actually execute. So nothing actually gets executed here because main is empty. But yeah, so here. Comp sci student is a sub trait of both programmer and student. Implementing comp sci student requires you to implement both super traits, programmer and student. Programmer and student. Okay, fair enough. All right, that's understandable. Disambiguating overlapping traits. Of course, traits that have the same get. Which get are we going to use, for example? Because each trait implemented gets its own impl block. It's clear which traits get method you're implementing. What about when it's time to call the methods? We have the full qualified syntax. And what's the full? Oh, yeah. Form as age widget get. Form as username widget get. Okay. So the as, angle brackets, double colons, whatever. Cool. Lovely. Okay. Happy with that. And that is that. We're going to move on to macro rules next time. Okay. Because that was enough about traits. All right. Thanks for hanging in there. Talk to you next time.